Welcome to Intelligent Systems, an introduction to artificial intelligence. In this video, we will look into a key aspect of neural network training, gradient descent. It's the key innovation that is at the heart of backpropagation, which makes it efficient to train neural networks. So let's look back at how we view neural networks. They're a function of w of x equals y, and they have a special organization in that we have input neurons, output neurons, and hidden layers in between. And as an example, let's remember again a function of w that takes an image as input and produces as output the digit 5. So how can we define the function fw? And we will proceed in 3 steps in doing so. And we will look at how we can move from a random assignment of weights w to an optimal assignment. We will do this in a linear regression setup. And then we will see in the second step how we turn a regression into a classification. And then we see in the third step how we move from a linear setup to a nonlinear setup. So in this lecture, we will just look at the first aspect, how we can use gradient descent to move from random to optimal weights. So the technique is called gradient descent, and it allows us to find those weights w. And what is very important, we will demonstrate gradient descent here in a very, very simple neural network. So we will not use the complex structure with many input neurons, many output neurons, and many hidden layers in between that we were discussing conceptually so far. But instead, we focus on something super simple. There's just 2 input neurons, and one is actually a special input neuron. It's called the bias because it's not even multiplied with an input value. It just contributes a weight without any x. And the second one does have a value x, an input that is given, and that's weighted with w1. And then the sum is computed, and we don't even have an activation function after computing the sum of those 2. We have our value y as output. So essentially, we have a very simple linear function, fw of x equals w1 times x1 plus w0, and that equals 2y. And what is very important here, we will demonstrate in detail the principle of gradient descent in this linear regression setup. But of course, it's not that neural networks do linear regression, right? And we will see what the neural networks do then in the next steps 2 and 3, where we move from regression to classification and where we move from linearity to non-linearity. But that's for the next video. So how can we change our weights? How can we find a new w1 and a new w0? And the key problem that we're having is into which direction to change the weights. And that is so important because it would be very compute intensive to test really all possibilities of directions into which we might be changing. So instead, we want to figure out the direction in which we have the steepest descent of our loss function. And let's see how we do this. We look into a specific example scenario of flat sizes and flat prices. So our x values are flats and square meters, here 60, 120, 180, and we have prices like 150,000, 300,000, 400,000. So visually we can depict this as here, for example. This is a data set of about 50 flats, and you can see here size versus price plotted, and you see that that is somehow linear, but it's fanning out towards the more expensive prices. By the way, this is synthetic data. Whether it's in any way realistic, it probably isn't. So over the next slides, xj denotes a flat size, yj star denotes the known price, and yj is denoting the predicted price. And j is running from 1 to n, and in this specific case, n is equal 50. So what do we want to find? We want to find a linear function that can serve as a predictor for the flat price. And you see already that over here in this region, it's doing quite a good job, this red line, towards the more expensive prices. The error is sometimes a little bit bigger, but sometimes it's also quite good. So if we want to find a good predictor, we have to have a way to judge a regression line that we have defined. So if we get, for example, these two here, the one on the left and the one on the right, we have to have a way to say that the right one is the much better one. And one way of doing this is the mean squared error, which we have mentioned already in the previous lecture. So this will be our loss. So what is the mean squared error? We go through point by point and we measure the difference between the predicted and the known value. So if we zoom into the figure of the previous slide, we've seen here some of the known values. These are the blue dots and our regression line. And what we do is we measure that difference here between the regression line and that known value. So that was actually only a very small deviation. But if we go to this point here, the deviation between predicted and real was already quite much bigger. So we measure all of these differences and then we compute the square because we want to increase the impact of large errors and we don't want to penalize that strongly small errors. So this one we say, yeah, that's about fine, but this should have a heavier penalty. And then we compute the mean over all of these values, and that's what we want to maximize. And by the way, that's quite interesting because you saw in the linear regression that towards the cheap flats we were making less error, and towards the more expensive flats it was kind of fanning out and the errors were bigger. So it's actually quite an interesting concept to say that we build the mean over all of them. And you could imagine other loss functions where we give emphasis and say we're actually mostly interested in the flats between 90 and 120 square meters and less interested in the bigger ones, and also in the small ones we're not so interested. But for the sake of practicality, we stick to a very, very widely used measure, and that's the mean squared error. So this is what it looks like in a formal way: 1 divided by n, the sum running from j1 to n, and we build the difference here, j star y star j minus fw xj, and that is squared. So just to show again what that means, and that mean squared error is really a very, very good name for this formula because it explains the formula one-to-one. You don't have to learn it by heart. So here we're building the mean value with the division by n and the sum that we're computing. Oops. Here we're computing the error, that's the difference between the known value and the predicted value, and we're squaring the whole thing. So mean squared error is a perfect name. And just to remind you, n data points, so the n is showing up here, y star is the price of the flat, xj is the size of the flat, and fw from xj is the predicted price of the flat. So now, before we look into detail how we're going to do the gradient descent, we have to refresh a little bit of math, and I really highly encourage you go back to your math books and do that. We will use for the next couple of lectures some derivatives. And generally we follow the notation delta f over delta x, and this was introduced by Newton from your math lectures. You may remember Leibniz notation f prime, but for some reason, since neural networks also have a foundation in physics and Newton introduced calculus with a physics view, we're going to follow this Newton style of writing derivatives. Although, mind you, of course, Leibniz also used this delta. And the Newton style of writing derivatives, maybe as a little side-on, is quite interesting. In your physics classes, you use the notation x dot, and in your math classes, you used f prime. And that's exactly the difference between Newton and Leibniz, who both introduced calculus at the same time, but using different notations. Okay, so be it as it may, we denote the derivative by delta f over delta x. And very simply, if we have a linear function delta x over delta x, then the derivative is 1. If we have a squared function delta x squared over delta x, then that is 2x. If we have a sum delta f plus g over delta x, then that is delta f over delta x plus delta g over delta x. And we have the chain rule. If we have f applied to g and build the delta over delta x, then this is equal to building the derivative delta f over delta g times the derivative of delta g by delta x. And if Leibniz notation, this would be fg of x prime is equal to f prime of g of x times g prime of x. So let's start very simple with our function fwx, which was the linear regression, equal to w1 times x plus w0. Now, if we would build the derivative by delta x, which you can see over here, then it is w1. However, we're actually not really interested how the function changes with respect to the input. What really interests us is how the function changes with respect to the weights. So let's therefore build the derivative to delta w1, and that is actually x. And if we build it to w0, that's the constant 1. Now, we wanted not just the linear regression, but we wanted the error over the linear regression, and that's why we're now making this formula a bit more complex. So let's look into the difference between the known value and the predicted value for which we just did the derivative. So, and again, nothing much changes because the known value is a constant when it comes to w1 and w0, and that just means that if we take that difference, that means the error between predicted and known, and build the derivative by w1 and w0, we get exactly the same results, namely x and 1. Okay, now let's get the square integrated into the error and build the squared error. So here we have the delta for the squared error by delta w1, and now we see we get 2 times, and then we get the difference of the error times x, and in the case w0, where there was no basically input value x associated, we see the x is missing because it's a constant, and we just get 2 times the difference between the known value and the predicted value. Okay, but what we wanted was the mean squared error, and that means we want to sum up all of the individual errors and build the average over that. That means we have delta 1 by n, and then the sum over all of these errors by delta w1, and then we see, well, that was easy. The sum of the derivatives or the derivative of the sum is the sum of the derivatives, and we can apply that here, and that means we get 2 divided by n times the sum over all of the errors of the predicted and the known values, and for the case of w1 times xj. So that's important. That's here within the sum, and this is a j over here, and this is xj over there. And for w0, that xj is missing, and the rest is the same. So, and that's actually quite important. So we have now achieved already a computation of a delta E by a delta W. Yeah, E is our error, mean squared error here in this case, and as I said in your network terminology, we always abbreviate the error by E, so we have here delta E by delta W. Now, let's do the next step. What we really wanted was the update function, how to adjust the weights. That's what we tried to answer. And what we now do is that we have an iterative process in which in each step we add the derivative of the mean squared error with respect to the weight, and we limit the change by a step size. And that means we get the update function w1. The new w1 is the old w1 plus step size alpha times the derivative that we just computed, delta E by delta W, and the same for delta 0, with the only difference being that here the xj is missing in the sum. So we have implemented our first update rule for W. So now let's take a look how good this gradient descent actually works on our flat sizes. Can we get the linear predictor that was doing quite a good job, as we've seen it already in the introductory slides. So here you see the animation, you've seen the plot with our examples, and starting here from this predictor in a lighter pink, and from each update of the weights, it gets into a darker red. And you see this is the progression here from the bottom to the top. So we're not starting with a random assignment of weights. We're starting with weights that are set 0. So W1, W0 are both set to 0. And as you can see, essentially we're predicting that any flat is up there for free for €0. That is not a very good predictor. That is not very much like the reality. And now you see that bit by bit we make improvements, and you can see already that in the first steps the improvement is really quite large, and then as we get closer to the real values, the improvement gets smaller and smaller and smaller. So we can see there is a principle of convergence of reaching the best linear regression for our given points. And we can look at this in a more detailed way by systematically plotting all of the weights against each other. So you see here on the X and Y axis, W0 and W1, and we have limited the ranges from 0 to 5,000 for W1 and from 0 to 40 for W0. And the orange dots are the losses that you would incur if you were using these W0, W1 configurations. And in blue, you see the errors that were accumulated by the W1, W0 configuration that the gradient descent has actually depicted. Yeah? So basically, the blue dots represent the loss per epoch for our gradient descent. And again, in the beginning, our weights are set to 0, and that means the first point is here at the position 0, 0 over there. And then you see how gradually here, for example, the point is close to 1,000 over there, and it's a bit difficult to see in 3D. It's probably around 5 on the W0 score, and bit by bit you see this trajectory as it's moving into this direction. Now let's look at the loss function by itself, and let's look at it in the context of the epochs that we're running. So remember, an epoch was a full run through all of the experiments. Here it was examples. Here it was just 50 examples, and that means our batch size is equal to the epoch size, and that means we're looking at all of the examples of one epoch, which was just 50, and then do the update. This would change if this was like a big a website that like Immobilien Scout or something with thousands and thousands of training examples, then probably we would set our batch size at 256, and our epoch would consist maybe of millions of examples, and then batch versus epoch would really make a difference. However, since this is a toy example, we leave it at 50, and we just make one batch equal to one epoch. Okay, so over 12 epochs, you see this behavior. At the beginning, a very big improvement. The loss reduces from over 80 very, very quickly in just 4 epochs to something less than 10. And then it seems to be converging and is actually pretty close to 0 towards the 12th epoch. Now, why is this technique called gradient descent? And I think if we look at the 3D plot, then it's pretty easy to understand why it's a gradient descent, because we walk along the gradient of the loss function towards the minimum. So this is the loss function over here, and somewhere over there must be a minimum. On this line over here, that's where it's pointing at. And we start somewhere high up in the mountains, and bit by bit we go deeper and deeper into the valley. So it's a descent, and the descent is happening via the gradient. Now, when you look at the orange plots, then that looks pretty much like a polynomial. It looks pretty much like this curve over here, which is a quadratic function. And now, is that actually always a polynomial? Is it actually always quadratic? And when we look at it, it looks quadratic in W1. So this pretty much looks exactly like this curve over here, but it doesn't look quadratic in W0. So if it was quadratic in W0, then we should get something looking like this over here. So why is that? So, and the answer is, well, yes, indeed, this is looking quadratic. And the reason that it's looking quadratic is that our error function was the mean squared error. Yeah, so we do have the square in there, and that produces this peculiar shape. Now, and the reason why we don't get the symmetric vase over here is that W1 and W0 are on two completely different scales. So you can see here it's ranging from 0 to 40. Over there it's ranging from 0 to 50. If you would plot W1 and a range of 0 to 40, then you also would not really see much bending and the strong descent. Yeah? Whereas if you would zoom out and plot here W0 from 0 to 5,000, then it would become more closely looking to such a vase. But of course, this vase doesn't have to be symmetric. It can be elongated and can take many different shapes. But the key aspect here is that you understand that this quadratic looking nature is coming from the error function that we use. And if you would use a different error function, then this error landscape would of course look differently. Now, another aspect is the assignment of the step size alpha. So if we make alpha too large, then we will overshoot and not find the minimum. And if we make it too small, then we will not reach the minimum. Let's look at our setup, what this actually looks like. So here we have set the step size too large. And what you see is that the configuration that steepest descent picks is jumping between something close to 0, 0 and something close to 45,000. Yeah, and it's jumping between those values. And when you actually take the order how these dots are produced into account, is actually not going from here to there and then bit by bit maybe jumping and getting closer to the minimum here. No, it's actually getting worse. You know, we're starting off here at 0, 0, and it gets worse and worse and worse and worse. And that's what you see here as we plot the loss over the epochs. We wanted this to be starting at very bad and then getting better. And in the previous example where it had worked very nicely, very bad meant 80. And look at here, we're starting at 90. Or, yeah, no, probably it is 80 here. It's actually the same value as we had previously, so it is 80. But instead of getting better, we see here things get worse and we end up with an error of 140. And you can see that also over here visualized in the predictors that we're actually creating in the context of the data, that the first one is over here, that's the 0, 0 line, and then it's just jumping at a complete overestimation to a complete underestimation, including even negative prices. Wow, what a great world that would be where you get a flat and they even pay you money for taking it. Now, what happens if we make the step size too small? Well, then we cannot reach the minimum, and you see that depicted over here. We're starting at 0, 0 here, and these are our iterations. So we are going into the direction of the steepest descent, but we're only making very slow progress. And you see that over here, yes, there is progress, but it's not very steep at the beginning, and then it's tailing off. It's continually going down, and that's an indication that our step size is too small. And again, you see that over here, after 10 iterations, we did get closer, but we still don't really have a good predictor. So that is something that you really should take on board. So this slide you should remember. If you plot the loss against the epochs, then you should judge the degree of convergence of the loss function. And you should adjust the step size accordingly. So here to the left, that is when the step size is okay. That's exactly how it should be looking. This is an indication that the step size is too large, and here the step size is too small. And the tricky bit is, of course, that this is really engineering. You have to figure that out. Of course, you can try to automate the configuration and the checking of different step sizes, but again, you will not be able to test all step sizes. You have to experiment. So that brings me to the conclusion. Gradient descent is an engineering task, and that requires experience. And what makes it difficult and an engineering task is that you have to set the step size, you have to determine how many epochs you want to run this, you have to set the batch size, you have to choose a loss function that is appropriate, and you have to decide how many data points you want to process. So all of these are variables that influence the predictor that you're generating and how good that predictor will be. And getting the right balance between all of these different aspects is an engineering task. So as a take-home message, you should understand the concept of gradient descent, and it's a technique that allows you to minimize a function. And in our example, it was an error function, the mean squared error, but it can be any error function. And in fact, it can be any function at all. In the labs, you will look into more detail into that and just take completely different mathematical functions and minimize them. You should understand how to compute the derivatives for the mean squared error. You should understand how the loss is decaying over the iterations and which role the step size and the epochs are playing in this. And you should be able to engineer a decent descent.